Okay, so if I hook up this, what's the simplest sort of network I can imagine here? Where I'm going to put in one p-channel device and one n-channel device, like so. So here's my input node here. Here's my output node. Here's VDD. Here's my ground connection. So let's build that device. That device has, first of all, notice the schematic symbols. This is an NFET. And this, the same picture, except with a little bubble on the input to remind us that it's inverting. In almost all logic diagrams, those little bubbles mean invert. So this means that this switch is conducting when the voltage is high. This switch is conducting when the gate voltage is low. So how does this work? How does this device work? If I put in a low voltage on the input, so if I put in a 0 here, what happens to the output? So think it through. If I put in a low voltage here, is this switch on or off? This guy is off. How about the PFET? He's on. She's on. It's on. Okay. So what happens to the output node? It gets pulled up. In other words, there's a conducting path between the power supply voltage and it. So this guy will actually turn into a 1. Okay, so a 0 in produces a 1 out. What about if I put in a 1 here, a high voltage? I'm just going to use our sort of symbolic name for it. It's what the power supply voltage. Now what's off and on? So how about the n-channel pull down? It's on. The n-channel pull up is off. And the output node is connected how? Through the pull down network to ground, so it will go to 0. So what I've done is, using my voltage control switches, I've made a little device that you put in a 1 or a 0, the voltage corresponding to 1 or a 0, and what happens to the output? It inverts it. This is called an inverter. Okay, and we're going to build some other logic functions in a moment using more complicated switching networks. But in general, we're going to use these switching networks to make the output charge up through the pull-up path or pull down through the pull-down path, okay, as best we can. Now, my question to you is, what happens if I put an intermediate voltage in there? Well, they're sort of, you're not quite sure. I haven't given you enough information to really figure it out. But the choices seem to be they're both off. What happens to the output node when they're both off? Well, it's not connected to either the power supply or ground. But what happens? So what does that mean? It's floating. In other words, floating is just another way of saying it's not connected to one power supply rail or the other. What would happen to, suppose I had charged it up, so it was sitting here at a 1 value, some high voltage, and then I turned off both guys. What would you expect to happen? So if it's not connected to either ground or VDD, you'd expect it to sort of sit there and float at 1. Remember, this wire here, which goes off to other places, has some amount of capacitance. So we're essentially storing some information on the output node here. And not very reliably, because there's a small amount of leakage current that happens here. This guy, when I said he was off, I was lying. There's actually a couple picoamps of current that flow, enough so that that node will eventually get discharged. Okay, but over the course of, say, tens of milliseconds, that node will maintain its value. What happens if they're both on? What can you tell me about the output? If I have both, if I have a pull-up connection and a pull-down connection at the same time, yes? Okay, so there's a couple things. One, from a logical point of view, we probably will produce some sort of voltage sort of in the middle, which is a forbidden voltage. In other words, we don't expect a logic output from this. Okay, I'm using my battery to drive this connection. I have really bad news for you. What's the really bad news? I have a short between power and ground. And I'm dissipating power like mad. And how much power depends on the resistors, the resistance of those channels, right? So the devices you own actually have billions of these FETs in them. so that means I could actually get a pretty substantial short. So as I'm designing these pull-up and pull-down networks, if I want them to behave as logic gates but never to create a short, what do I have to guarantee? Well, that they're never both on at the same time. That would be a real disaster. Okay, or if they're on at the same time, they're only on for very, very small fractions of a second, you know, a picosecond or two. Okay, so when I design these networks, I'm going to have to design them to be complementary. In other words, if one is on, the other is off, and vice versa. So that's the whole story behind complementary logic. Here's a picture of the VTC of a CMOS inverter. You can see that it does pretty well. It's very close to the ideal, right? It has a very large gain in the middle. Okay, so we just sort of went through this, right? When I put in a low input voltage, the output voltage is high because basically the pull up is on and the pull down is off. And similarly, when I put in a high input voltage, the input voltage is at this range, the pull down is on, the NFET is on, but the PFET is off, so I get a very low output voltage. Okay, and in the middle, I get this sort of quick change. And so I'm going to do my Valentine in just a second, but let's stop here for a second. There's one other thing I want to point out. Okay, what happens when the input is 1 here? This output node will eventually discharge all the way to ground. In other words, it's connected through this voltage control switch, and it will eventually discharge all the way to the ground. At that point, are there any currents flowing in this network at all? When there was a positive voltage here, then there was a potential across this channel resistor, and so discharge happened. But when it finally gets all the way down to 0, what can you tell me about the amount of current flowing in the network? There shouldn't be any flowing because there's no potential difference across the source and the drain. There's no potential difference across the resistor, meaning there's no current flowing across the resistor. V across the resistor is 0, so I across the resistor is 0. Right? And so what this tells me is with this particular circuit configuration, modulo little, some issues with leakage current, assuming there's no leakage current, once I've discharged that output node, no more current will flow. And the reason that your watches last a whole year in a tiny little battery is because there's no static power dissipation. If nothing is changing, if no values of the signals are changing inside of the circuit, there's no power being dissipated by the circuit. So not only, okay, do I have a very high gain, okay, I have VOHs, which are very close to, in fact, almost exactly the power supply. I have VOHs, which are very close to the power supply. VOLs, the output low, which are very close to almost identically ground. Okay, so I end up with great noise margins. Great noise margins. So here's, apropos of probably Thursday. Okay, why do we love CMOS? Okay, and this is really part of the take-home message, right? Oh, CMOS, let me count the ways. Okay, so the one thing is that it has a very high gain in the VTC, which means I get great noise margins. And what do I mean by great? I mean large. Large noise margins. Your girlfriend will expect, or boyfriend will expect something a little bit different than this, but as engineers, this is what we love. Okay, so, and then the other thing I wanted to point out is that VOL is approximately 0 volts, and VOH is approximately the power supply voltage, and that means that there is no static power dissipation. In the steady state, no currents are flowing. Okay, that's not true of every logic family. In fact, it's not true of almost any other logic. The reason CMOS has been king for so long is these two items. Everybody understand why we send a Valentine to CMOS? Why the digital world has happened and we carry it around in our pocket is because of these characteristics.